Hi, everyone. I hope that you are doing well. My name is Professor Andrew Timming, and I want to extend a very warm welcome to you for dropping into this lecture. This lecture is Chapter 8, Lecture 1, corresponding to the textbook Applied Statistics, Business and Management Research. And in this lecture, we will be focusing on two interrelated research methods, simple regression and Pearson's R, also commonly referred to as Pearson's R correlation coefficient. This is the last of our bivariate tests that we'll be looking at in this textbook. From here on out, from chapter 9 onward that is, we will be looking at multivariate statistical tests. But before we get to that point, it's important that you gain a good understanding of simple regression and Pearson's R. All right, let's get to it then. Here you can see the textbook that we'll be using in this lecture and for this course. It's entitled Applied Statistics, Business and Management Research. Hope you have enjoyed reading it and that you'll continue to enjoy reading it. This particular chapter, as I said, is chapter 8. So before you begin this lecture series, I would urge you to read chapter 8 because having read it will dramatically increase the amount of benefit that you'll get from listening to this lecture. Right. So we are jumping right into regression analysis. Regression analysis can be multivariate, as we'll learn about in the next chapter. But for now, we're looking at a form of bivariate regression analysis called simple regression. All right. So bivariate, remember, means that there is one independent variable, which we refer to as x, and another dependent variable, which we refer to as y. Regression analysis, what you will learn in this chapter, is arguably the most commonly used statistical method in the world. I've already mentioned that psychologists very frequently use ANOVA as their method of choice. But if you look at all of the different social sciences, if you look at psychology, economics, sociology, political science, etc., it is arguable that regression analysis is the #1 most commonly used method. Therefore, it's worth taking your time and really learning to understand this method inside and out. So we have two different, I guess you could call them manifestations of regression analysis. First, there's simple regression. And simple regression is what we use when we want to predict values of y from x, from our independent variables. So if we want to focus on the prediction of a particular outcome, we use simple regression. This is an unstandardized form of regression. Don't worry if you don't understand what that means. I'll explain it more later. Pearson's R, on the other hand, excels at explaining the nature of the relationship between x and y. So Pearson's R is a standardized form of regression, and it says something about the strength of the relationship between x and y. You can't use Pearson's R for purposes of prediction, but you can use it for explanation, and in fact it is ideal for explanation. So generally speaking, in simple regression and Pearson's R, the independent variable and the dependent variables are either ordinal or preferably scale in measure. And this makes sense because unlike chi-squared, which we just learned about in the previous chapter, regression analysis is a parametric statistical test. So once again, it is dependent on the, especially the dependent variable being normally distributed. There are three key questions that are asked in regression analysis, and we'll go through each of these in the next few slides. The first is there a generalizable relationship between x and y? The second is the relationship positive, negative, or neutral? And the last question is, how strong is the relationship? So let's start with the first question. is there a generalizable relationship between X and Y? So this is, I guess, the same question you would ask in any inferential statistics test. We ask the same question when it comes to chi-square and ANOVA and t-test. But let's think about how we might answer this question in the context of regression analysis. So most data, when you do a regression analysis, it will show that there's some type of relationship between X and Y, right? It might not be very strong, but there will be some kind of identifiable pattern of a relationship. But the question that we're asking is not whether or not X and Y are related in our sample. We don't care very much about our sample. What we care about is whether our relationship between X and Y in our sample generalizes to the wider population. And there we go back to the importance of the p-value that will accompany all forms of regression analysis. So the key question is the relationship between X and Y generalizable, or is it simply an artifact of our sample data? Now, what we do when we do regression analysis is we produce a coefficient, or sometimes this is referred to as a weight. So this coefficient is a number that says something to you about the nature of the relationship between X and Y. In simple regression, the coefficient or the weight that we use is referred to as b. That's a lowercase b. And this is an unstandardized weight, an unstandardized coefficient, meaning it has no limited scale. It can go up to infinity and it can go down to infinity in the negative side. Pearson's R, on the other hand, also commonly referred to simply as R, is a standardized coefficient. It is a standardized weight. It is always a number between -1 at the lower end and 1 at the upper end, which is why we tend to use Pearson's R for purposes of explanation. But whether we're using simple regression or Pearson's R, in both cases, what we want to do is not only look at the coefficient, but also the p-value that's attached to that coefficient. And if the p-value is less than 0.05, then we will assume that the relationship between X and Y in our sample is indeed generalizable to the population. Okay, so the next question, beyond is there a relationship that's generalizable, is the relationship that we found between X and Y a positive relationship, a negative relationship, or a neutral relationship? A neutral relationship is another way of saying that there's no relationship between X and Y. Now, a neutral relationship would be a case where your coefficient B in the case of simple regression, or your coefficient R in the case of Pearson's R, is roughly equal to 0. In other words, your p-value is greater than 0.999. And you can see a neutral relationship depicted at the top right of this slide. You can see the line of best fit is purely a horizontal line, meaning that as values of X increase, there is no effect on values of Y. Now, in practice, as I said before, when you collect data, you're almost always going to find some level of either positive or negative relationship between X and Y. And that can be a weak relationship or that can be a strong relationship. Now, when B and R are positive numbers, right? So they're positive numbers, then we can assume that the relationship between X and Y is a positive relationship. And you can see that demonstrated in the second graph on the right-hand side of the slide, the line that's sloping up. So in a positive relationship, we can see that as values of X increase along the X-axis, you can also see a concomitant increase in values of Y along the Y-axis, hence the upward slope. When your B coefficient or R coefficient are a negative number, when they have a negative value, then we assume that the relationship between X and Y is a negative relationship. That is to say, as values of X increase, values of Y concomitantly decrease. And you can see an example of a negative relationship at the bottom right-hand side of this slide. Now, the last question that we would want to ask ourselves in the context of regression analysis is how strong is the relationship, right? What is the strength of the relationship between X and Y? And this question is answered differently depending on whether you're using simple regression or multiple regression. So I'm going to start with simple regression. So simple regression in and of itself cannot easily answer this question. And the reason it can't answer this question is that the coefficient that we use to describe the relationship between X and Y, and this coefficient is called B, a little b, is an unstandardized coefficient, right? It has not been standardized. It is unstandardized. So what does this mean? What this means is that the values of B are dependent on the scales of the variables that were used to measure the constructs that are in your equation. So B is intimately related to the measurement scales that you use for the variables that you use in the equation. So higher or lower B values don't necessarily imply a stronger or a weaker relationship. The only real measure of strength that we have in the context of simple regression is the p-value, right? So you can see a positive b value, whatever that is, if that has a p-value that is statistically significant, that is to say less than 0.05, then we're going to assume that the relationship between X and Y is statistically significant, whether that relationship is positive or negative. Now, when we ask the question, how strong is the relationship, and we're using Pearson's R, we can very easily answer this question, right? In comparison to simple regression where it's difficult to answer that question. Pearson's R, unlike simple regression, is what we call a standardized test statistic. A standardized test statistic is a test statistic that no matter what scale or configuration of variables you're using in your equation, the result of the analysis is always going to be a number between -1 and 1, meaning that no matter what kind of configuration of variables you're using in your regression analysis, if you're looking at the result using Pearson's R, there's always going to be a floor of -1 and a ceiling of 1. If you've done the math and you get a number that is less than -1 or greater than 1, it means that you've made a mistake somewhere in your math. So the interesting thing about Pearson's R is that as with B, a Pearson's R of 0 would indicate no relationship at all between X and Y. But as you get from 0 up to 1, the closer you get to 1, the stronger the positive relationship between X and Y. And similarly, as you move from 0 to -1, the closer you get to -1 for your coefficient, the stronger the negative relationship between X and Y. So if your beta coefficient or your Pearson's R coefficient is 0.3, right, that would indicate a weaker relationship than if it were, say, 0.7. Similarly, on the negative side, if you had a Pearson's R coefficient of -0.2, that would be a weaker coefficient than if it were -0.8. So the closer you get to 1 and -1, the stronger your relationship, which is why if you're interested in looking at the strength of the relationship, Pearson's R is a better method than simple regression. Sometimes it helps to visualize regression analysis because it will give you a better sense of what goes on when you do a regression analysis. And the best way to visualize a regression analysis, especially a bivariate one, is through what we call a scatter plot. You can see an example of a scatter plot at the bottom of this slide. You can see a line sloping upward through these data points. And what we call this line is the line of best fit. Sometimes it's also called the least squares regression line. And what this line represents is the absolute least distance between the line itself and every other data point in your data set. So what we're trying to do is to minimize the distance between the line of best fit and the data points in your data set. So there is one line that you can draw through these data points that will represent the line of best fit. And if you calculate the distance between each individual data point, these dots on the scatter plot there, and the line itself, each one of those is called a residual, right? So it's a residual, it's an error term. And what you want to do when you fit a regression line is to identify the line that best minimizes the residuals given whatever configuration of data that you're using. Now, it's important to remember when you're doing regression analysis that correlation, if you find a correlation, is not the same thing as causation, right? So just because you find that X is statistically significantly related to Y, whether that's in the form of a positive relationship or a negative relationship, we still can't conclude on that basis that X causes Y. So if we find, empirically speaking, that two variables are correlated with one another, X and Y, what we can say is that these two variables co-vary, right? There's a covariance between the variables. And if X is significantly correlated with Y, we know that in a positive relationship, as values of X increase, then values of Y simultaneously increase. And in a significantly negative relationship, we know that as values of X increase, values of Y similarly decrease, right? So as X goes up, Y goes down. But remember, just because we find a statistically significant relationship between X and Y, what we can conclude is that these two variables are significantly associated with one another, right? They're significantly related to one another. But we can't conclude that they significantly cause one another. In other words, we do not know, nor can we infer that X causes Y in any way. Let's take a few moments to think about some research questions that we could both ask and answer using simple regression or Pearson's R correlation coefficient. Is time on social media negatively correlated with mental health? Right? So we might assume that the more time an individual spends on social media, the worse his or her mental health. So in this case, our independent variable is the amount of time that you spend on social media, and the dependent variable is some measure of mental health. How about, is income positively correlated with motivation? Right? So as income increases, are employees more motivated in their work? In this case, the independent variable would be income, and the dependent variable would be some measure of individual motivation. How about on the other side of the coin, we could ask, is income negatively correlated with the number of written warnings that an employee receives? So in this case, the independent variable would again be income, and the dependent variable in this case would be the number of written warnings, and we might expect a negative relationship. In other words, as income increases, the number of written warnings probably decreases. And how about this last question? Is employee height positively correlated with performance appraisal scores? Right? So in this case, the independent variable would be employee height, and the dependent variable would be some performance appraisal score. Let's look at this last question in a little bit more depth. So looking at this research question, our independent variable would be the height of the employees in our sample, and our dependent variable would be their performance appraisal score, say, for example, in the previous year. So first question, what method would you use to collect these data? Well, for the first one, you could simply administer a survey to the employee and then perhaps to the employee's line manager. And the employee could provide the information on height, and the employee's line manager could provide the information on performance appraisal score. How would you measure employee height and performance appraisal score? Well, for height, you could use centimeters or inches or whatever kind of mechanism or method you wish. For performance appraisal score, it would obviously depend on the employees having some kind of metric score assigned to them. So for example, if they had a metric score assigned on a scale of say 1 to 10, where 1 would be the worst performer and 10 would be the best, you could use that particular measure in a regression analysis. And finally, what kind of relationship might you expect and why? My guess is you would probably expect to find that taller employees tend to have higher performance appraisal scores. In other words, you would expect to find a positive relationship. And why you might find this, you might have to go back to some evolutionary psychological theory about the powerful effects of height on various life outcomes. Obviously, one of those outcomes would be how you're perceived by others in terms of your performance. All right, thank you very much for tuning in, and I look forward to catching up with you at lecture 2. Thanks.